Look at the Pantheon. Its massive, unreinforced dome has sat under the Italian sun, surviving earthquakes, storms, and the relentless pull of gravity for 2 millennia. Compare that to the infrastructure we build today. It is common to see highway overpasses actively crumbling and relying on temporary metal supports just 50 years after they were poured. We have supercomputers and electron microscopes and advanced material science. So why does our concrete degrade in a few decades, while Roman engineering easily spans thousands of years? For a long time, researchers believed the Romans possessed a highly guarded chemical recipe that was simply lost to history. We know they used a specific mix of lime, seawater, and pozzolanic ash, a highly reactive material they mined directly from the borders of volcanic craters, like the areas around Mount Vesuvius. When seawater seeps into this specific blend, it triggers a chemical reaction. It causes rare minerals, specifically tobermorite and phillipsite, to rapidly bloom inside the structure. As these crystalline structures grow, they bridge the gaps created by microscopic fractures. The concrete actively seals its own cracks before they can spread. Instead of breaking down when exposed to harsh conditions, like crashing ocean waves, Roman structures use that water to repair themselves and grow stronger over time. While that chemistry is impressive, it isn't the only reason Roman concrete survived. Modern engineers actually know how to make extremely resilient concrete today. By adding chemical superplasticizers to the mix, we can drastically reduce the amount of water needed without losing the ability to pour the wet concrete easily. This allows the cement paste to cure into a much denser, high-strength material. Our infrastructure is failing because of what we hide inside of it. Concrete is exceptionally strong under compression, meaning it can handle massive amounts of weight pushing down on it, but it is remarkably weak under tension. If you try to stretch or bend it, it snaps. To solve this, we embed steel bars into the mold. As a heavy load bends a beam, the top compresses, but the bottom stretches. The steel absorbs that stretching force, holding the entire shape together. Steel is cheap, strong, and expands under heat at the exact same rate as concrete, but it has a fatal vulnerability. The moment moisture finds its way through the concrete's pores, the steel begins to rust. As iron oxidizes, it naturally expands. The resulting rust takes up significantly more volume than the original steel bar, creating immense internal pressure. It slowly forces the surrounding concrete outward in a process known as spalling. The exact same metal skeleton that gives our modern structures their flexibility ultimately shatters them from the inside out, guaranteeing their collapse. The Romans bypassed the problem of rusting internal reinforcements using a very simple strategy. They never used them. How do you build towering temples and massive aqueducts out of a material that shatters the moment it bends? You engineer the geometry so that the material never experiences tension in the first place. They relied heavily on massive gravity structures and arches. The steep curves and sheer weight of the stone ensure that all physical forces are driven safely downward into the earth. Every block is constantly being squeezed, never pulled. To keep everything perfectly compressed, they utilized brilliant architectural tricks, like carving out recessed, coffered ceilings to reduce the weight at the top of a dome and lower its overall center of mass. Ancient architecture survives because it pairs unique chemistry with an absolute dedication to massive, compression-heavy geometry. If we know exactly how to achieve a 2,000-year lifespan, it seems strange that we continue pouring steel-laced columns we know will crumble in our lifetimes. But the heavy geometry of an ancient temple cannot give us the sprawling, flat highway overpasses and slender, towering skyscrapers our society relies on. Those designs absolutely demand the tensile strength of steel. Furthermore, building every new piece of public infrastructure with the sheer, redundant physical mass of Roman walls would bankrupt modern taxpayers. Today, material scientists are looking for a compromise. They are actively experimenting with adding pozzolanic ash and similar industrial byproducts into our modern mixes, trying to give our steel-reinforced designs the ability to heal their own microcracks before moisture ever reaches the metal. The stakes for this research are high. Traditional cement production requires enormous kilns, accounting for roughly 8% of all global carbon emissions. Adapting ancient volcanic recipes could drastically cut that environmental footprint. We didn't lose the secret to building structures that last 2 millennia. We simply made a choice to prioritize the versatility, cost efficiency, and scale required by the modern world.